9.2b, we're going to look at a two-sided test for a proportion. When the accounting firm AJL & Associates audits a company's financial records for fraud, they often use a test based on Benford's law. Benford's law states that the distribution of the first digits in many real-life sources of data is not uniform. In fact, when there's no fraud, about 30.1% of the numbers in legal or financial records begin with the digit number 1. However, if the proportion of the first digits that are 1 is significantly different from 0.301 in a random sample of records, AJL & Associates does a more thorough investigation of the company. Suppose that a random sample of 300 expenses from a company's financial records results in only 68 expenses that begin with the digit 1. Should AJL & Associates do a more thorough investigation? So is it enough different than 30%? Well, let's find out. Now, before I jump into state, plan, do, conclude, I need to decode the question. There's a lot of words and there's some numbers in there. I need to identify what these things are. So the first thing I come across is this 30.1. Okay, this is the claim. This is what the law says, that it's about 30.1% of the numbers begin with a 1. Since this is the claim, this is the p-naught value that I'm going to use in my null hypothesis. Okay? Now then it says, if it's significantly different from indicates a not equals to. That's what I will use in my alternative hypothesis. Same value for p, but the inequality has changed. It will always be equal in the null, and the alternative will always have the not equals, greater than, or less than. Now, what else does it tell me? In a random sample of 300 expenses, 68 began with a 1. So this is my p hat. It doesn't tell me the actual percent, but it tells me the 68 out of 300. That ratio is my p hat. And this is important, and we'll come back to this in a little bit, but I'll show you why it's important in a moment. But all this information we're going to carry on to the next slide because we're going to need it. All right, so let's do the state step. We want to test the following hypothesis at alpha equals 0.05 significance level. Our null is that 0.301, they claim. Alternative is that it's not equal to 0.301. Where p is the true proportion of expenses that begin with a number 1. Notice I've stated my hypothesis, my significance level, and I've defined the parameter. All three components are important in your state step. All right, in the plan step, I need to indicate what test I'm doing. So I'm going to perform a one sample z-test for p if the conditions are met, and then I run them through the conditions. First, is it random? It does state in the problem the expenses were randomly selected, so that's satisfied. And then is it reasonable to assume that there's more than 10 times 300 or 3,000 expenses in a company's records? That is reasonable, so I show that they are independent, the sample is independent. And then lastly, the large counts test. So remember, sample size times the value in our null hypothesis gives me 90.3, that's greater than 10. And then the sample size times the complement gives me 209.7. That's definitely greater than 10. This tells me that the sampling distribution of the sample proportions will be approximately normal, and I can continue on with normal procedures. All right, we're on the do step. So the first thing I need to do is calculate z. So I use my sample statistic that I got right here, subtract the null value, divided by the standard error. So I'm going to use the null value here and here, sample size here, run the numbers, and I get a negative 2.79. Now, we have a not equals to in our alternative hypothesis, which means it's a two-tailed test, right? So I got a negative z value. That means it's on the left. It's the left z value. The normal curve is symmetric, so the right-hand z value will be just the opposite. So if this was negative, this was positive. And the p-value that I'm looking for to draw my conclusion is the total area. So here's what's going to happen. I'm going to use my norm CDF to find the area of one tail and multiply it by 2. That's the p-value that I need. So here's how I handle this. I'm going to say 2 times the p-value that z is less than or equal to negative 2.79. So here it is, 2 times norm CDF. Okay, there's my lower bound, my upper bound. My mean is still 0. My standard deviation is still 1 because I have standardized it. And this is the p-value I come up with. All right, so there's the p-value. Now we draw our conclusion. We connect that p-value to the alpha. We said because the p-value is 0.0052 and that's less than 0.05, we reject the null. P is low, we reject the ho, right? There's my first sentence. Second sentence has to have context and talk about the evidence. So we reject the null, so there is convincing evidence that the proportion of expenses starting with a 1 is not 0.301. AJL should do a more thorough investigation, all right? Now, why do I say is not? Because that's what I said in my alternative hypothesis. Your second sentence will always just explain what the alternative hypothesis is looking for, okay? All right, can you use confidence intervals to decide between 2 hypotheses? What's an advantage to using a confidence interval for this purpose? Well, yes, you can use a confidence interval. And they actually give you more information about the population parameter. They give you an estimate, right? A range of values for the true parameter. So you can use that to make a decision, but it only works for a two-tailed test. It won't work if it's a less than or greater than test. It has to be a not equals to test. So let's look at this. Now in Benford's law, remember we just did this test and we concluded, we rejected the null hypothesis, okay, that the proportion, we found that there is evidence that the proportion is different than 0.301. So let's look at this. This is a 95% confidence interval for the true proportion of expenses that begin with the digit 1 for the company in the previous example is 0.180 to 0.274. Does this interval provide convincing evidence that the company should be investigated for fraud? So remember, to qualify for investigation, it has to be different than 0.301. That's the value, right? So I look at my interval. Is 0.301 within those values? No, it's not. It's somewhere between these two values, okay? So that is some good evidence that there should be an investigation because 0.301 is not there. So here's how I'd state my answer. Because it's not in the interval, it is not a plausible value for the true proportion of expenses starting with a 1. Therefore, the company should be investigated for fraud. So I want you to notice, you get the same answer using a confidence interval as you do with the hypothesis test. We concluded in the other one that they should be investigated, and that's what we concluded here as well. Now, can you use a calculator for the do step? There's a lot of work on that step. Can we use a calculator to shortcut some of that? Yes, you can. In your calculators, you would go to Stats, Test, and number 5. It says 1 proportion z-test. Make sure you don't choose 1 sample z-test. You want 1 proportion z-test. When you do, this is what pops up for you. First, it's going to ask you, what is the null value of the question? Then it's going to say, what is x, what is n? Well, the null value is what we used in our null hypothesis, right? The claim. Now, x and n, that's what we use to create our p-hat value, all right? In this question, we knew that 68 out of 300 was the sample they took, right? So my x is the 68, the n is the sample size. And then the last thing you have to say is, which inequality are we looking for here? In this case, it was not equals to the null value. So I choose the not equals to. Now, this is where students get lost on this using a calculator. Sometimes students want to put the p-hat value, the 0.227 here in for x. If you do that, it's going to come up with an error because x represents an integer. It's a number of people or it's a number of expenses. It's a whole number out of the total. So if you don't know what x is, you can find it by taking the sample size and multiplying it by the p-hat. And you'll see that as we go along. You can find it. You just need to remember that x has to be a whole number. So if you are having to calculate it, round it to a whole number. Now to show work on this, it's real important. When you hit the enter button on the test, this is the output it's going to give you, okay? It's going to give you the z-score, the p-value, and the p-hat value, okay? P-hat we already calculated. It should match what you used in the problem. So in order to show the work, you need to name the procedure, the 1 proportion z-test, show the test statistic, the z-value calculated, and show the p-value. My preference is that you write the equation out with those values in it, but the calculator is going to run the numbers for you as long as you enter in x and n and p naught in there correctly, right? So make sure you show work. Don't just put calculator gave me this. That won't work.